And hello everyone, I'm Peng from Johns Hopkins University, and today I'm going to talk about our new framework, Legolas, for efficient exposure of partial failure bug in large-scale distributed system. This is joint work with Haoze from Johns Hopkins University and Peng Huang from University of Michigan. Well, fault-tolerant distributed system can tolerate node crashes, and if a certain number of node crashes, the services can still hold. However, if too many node crashes, it's possible that all the services of the system will be down, and this is what we call total failure. Luckily, this type of failure can be quickly identified or repaired by existing mechanisms, thus limiting the failure impact. However, as to the partial failure, it's pretty troublesome. They often exhibit puzzling symptoms where the services seem to be available, but are partially broken. More formally, distributed system can be regarded as a set of services or list of APIs. Then we can define partial failure as a subset of it, fail to maintain its safety or liveness properties, while others still behave healthy. Actually, partial failure are pretty prevalent in production. They are hard to debug and can cause severe service degradation. Let me go through a real-world example to help you understand it. In one deployment of Zookeeper cluster, let's suppose that the whole cluster entered into a stale state. The clients experienced timeout in the create request, but get request still succeeded. Peng, the leader, also shows that it was live. It really takes a pretty long time for the developer to dig out the root cause. The snapshot thread at that time was dumping the data and stuck because of transient network issue. However, it holds a log and breaks the request handlers module. At that time, Heartbeat's thread is still alive to exchange a message with the followers, so there's no new leader re-election. Actually, there are many cases like this. In fact, a quite number of partial failure bugs are only triggered by fault events, so fault injection testing is really needed to catch them. They typically simulate faults while exercising a system with workload. Actually, fault injection has already been a popular practice. There are already some work to test the reliability of systems through randomly killing process, introducing packet loss, or simulating disk errors. However, as added to the task of designing a fault injection testing for exposing partial failure bugs, there are multiple challenges. The first is that the triggering faults often occur at fine granularity, like our previous example showed. To this end, the coarse-grained black box fault injection tools are insufficient. We should be aware of the specific type, location, and timing of the injected fault. And when your injected fault is the large distributed system, and when you care about the fault at fine granularity, the challenge of intimating injection space comes. Actually, in Zookeeper cluster execution, there are over 1,000 I/O fault candidates in only 1 second. What's more, in fault-tolerant distributed system, most injected faults will be masked. To this end, the random injection techniques are really insufficient. Some good heuristic need to be utilized to get the search. And here's our solution. It targets the two challenges we just talked about. It enables fine-grained inset injection through statically instrumenting hooks. It also, with the induced very large injection space, it also enables efficient search of it through extract a new abstraction on top of it and design decision policies on top of that. And here's the basic workflow. At the first static analysis stage, Legolas utilizes static analysis to add injection hooks and extract abstract states. The second stage is dynamic testing stage. Legolas will start a cluster of the instrumented system and run the workload driver. The same agent registered at each node will communicate with the Legolas server to inform the abstract states and ask for injection decision. Finally, failure checkers help users to inject the fault. Here, I'm going to elaborate on the three parts: fault injection hooks, abstract states, and injection decision algorithm because of time constraints. In the past work, there are already some work utilized node-level force interception approach to test the software. However, there are other to cause green or miss internal errors in the system. Legolas utilized static program analysis to deduce potential faulty conditions for each statement and add injection control points to directly simulate fault inside. Specifically, Legolas will leverage the straightforward method signature to deduce the fault conditions. However, it turns out that it's not that reliable. The first issue is that a method may internally throw an exception that is not declared in the signature. To handle this, Legolas performs intra-procedure analysis of the method body. It would analyze the arrow handlers in the function to only get the functions that exceptions that are uncalled or called and rethrown. What's more, because of the polymorphism and interface, there could be false positives. Just like the example shown in the picture, when the in-memory stream is taken as an argument, the write-int method of binary output archive is impossible to throw an error exception. To combat this, Legolas employs case-by-case inter-procedure context-sensitive analysis. To ease the afterward manual reasoning, Legolas instruments as deep as possible. It only instruments calls to either a method with explicitly through a statement or an external library function. The green one is the instrumented injection hook. During runtime, when it is reached, the agent will create a query to a controller and simulate the corresponding fault inside. So our operational fault module introduced exploding injection space. We really need some good heuristic to compress it. Our insight is that many fault injection attempts are not necessary because they are testing the similar situations. Take Zookeeper code snippet in the picture as an example. Sync request processor module continuously syncs the request to the disk, and occasionally when the log count reaches snap count, it will do the snapshotting. And the reproduction of the partial failure box in the previous example really need a fault injection inside lantern, the pink region. However, because the operation at line 6 is executed at each loop iteration, with the limited test resources, we may only inject faults at line 6. So the next question is how to define the system state for effective grouping. The complete execution states are obviously too excessive. A more reasonable representation to use some k-state variables to compress it. A value change of these variables then could indicate a system is in a different state. This representation, however, can still be excessive. Let's take another look at the previous example. Obviously, we can utilize log count as a state variable. However, most of its increments by one transition all induce the same information. So we really need a higher level representation for that. The higher level ones are called abstract state variables. In such representation, concrete state values do not matter unless they indicate a condition change at the code level. That is, trigger different code blocks to execute. Based on the intuition that they represent different stages of services in the system, we can just designate basic blocks as ASVs. And here's our algorithm that automatically extracts ASVs. Legolas first locates all the test unit classes in the system. These classes are generally threads or workers. We name them ASMs. The analyzer then runs ASV inference on each ASM. It treats all non-static, non-constant fields in the test classes as concrete state variables. Legolas then analyzes the main task method of the test unit class such as the run method of the thread. It finds a basic block in the task method that are control dependent on some ASV and treats each such basic block as a new ASV. You can see the paper for more details about the automation. And for the result, the figure really shows the ASVs that are inferred for the previous example. It pretty much catches what we would manually assign states for this chunk of code. It can successfully differentiate request handling and snapshotting in separate 2 stages. As to the implementation for each inferred ASV, they analyze the instrument's call to the Legolas agent. At runtime, the agent notifies the Legolas state tracker of the current abstract state. So with the inferred abstract state, Legolas enables stateful decision policies on top of that. When the controller receives an injection request from the Legolas agent, the controller checks which abstract state the target system is in at that time to make decisions. We have 2 considerations here. The first is that it's difficult to learn if a state is interesting beforehand, so we should not focus at one state too much. What's more, there can be multiple injections inside only one state, and our buggy point may not be the first request. And here's our solution to tackle the 2 challenges mentioned. Budget state round-robin policy. Round-robin feature is for the first consideration, and the budget is for the second one. The initial budget for OSV is set to n, and each trail would only focus on one ASV. This means that only an injection from the ASV would be accepted, and injections from all the other ASV will not be allowed. And after each trail, if an injection is granted, decrease the budget by 1, and then move focused ASV to the queue end. Also, the round-robin list is dynamically adjusted. If an ASV is unseen before, append it to the queue end. If an ASV's budget is used up, remove it from the queue. After all ASV budgets are used up, refill all ASVs. For the injections within the same state, we utilize randomization. The probability P per state should be set properly. If it's too large, we would always grant the first field request. If it's too small, we may waste the injection trail. The formula shown can make sure that the probability that all C injections are not granted is equal to 0.01. So to evaluate our framework, we evaluated on 6 widely used large-scale distributed systems. This system have different functionalities written with various programming paradigms. Due to the large scale of experiments and time constraints, we'll only focus on the following 3 faults: error-related exceptions, custom exceptions that extends L exception, and delay of function calls involve disk or network I/O. And the results show that Legolas successfully applies on the 6 systems. The number of task classes Legolas extracts is much smaller compared to the number of classes in the system. Zookeeper has the largest ASVs per ASM. This is because Zookeeper uses long-running threads, while Cassandra adopts an event-driven architecture that uses mainly short-lived threads. The mean ASVs per ASM is moderate because currently Legolas only analyzes the task interest method. This is the most exciting part. Legolas finds new bugs in all tested systems. It finds 20 unit bugs. All bugs are non-trivial and require domain knowledge to understand, such as mishandling of errors, design flaws, and synchronization issues. They all cause partial failure symptoms, and the root cause of them are pretty diverse. We reported the bug to the developers on Jira. 11 of them are explicitly confirmed by developers. Here's one bug case in HDFS found by us. It causes situations that one client gets stuck without any error log, and the workload progress is partial, while other clients finish their workload successfully. Through code analysis, we find the root cause is a complex timing bug. Legolas exposes the bug 5 times in the experiment, with the first time in trial 124 at around 43 minutes. To further validate our thesis, we compare the BSRR algorithm with alternative decision policies on the 20 new partial failure bugs. For each policy, we run the 2000 trial experiment and measure the number of exposed bugs and the time spent. The new state-only policy exposes 8 bugs in the median of 11 minutes. It's the best among the baseline policies, showing the advantages of our inferred abstract states. The BSR significantly outperforms alternatives. It exposes 20 bugs in the median of 58 minutes. It is more robust in leveraging the imperfectly inferred abstract states. We also compare Legolas with 3 state-of-the-art fault injection research projects that target exposing failures in large-scale distributed systems. The first 2 works focus on no-level or IO-level faults, making them not directly comparable to Legolas. We apply their key ideas to attempt meaningful comparisons. With the same workload, they are not effective in exposing the partial failure Legolas found. Partial failure bug is prevalent and severe in large-scale distributed systems. The existing fault injection techniques are really insufficient in exposing them because of the granularity issue. So we developed Legolas for exposing partial failure bugs. It utilized static instrumentation to enable fine-grained inside injection. With the induced very large injection space, it automatically extracts the new abstraction, which we call ASV, and utilize decision policies on top of that. And our framework, Legolas, is open source. If you feel uneasy about your implemented system, yeah, just try it. You only need some scaffolding information. Yes.